In December 2015, multiple countries unite under one banner, the Paris Agreement. The accord sets goals to limit temperature increase to less than 2 degrees centigrade within this century. A big contributor and an area we're trying to help is transport. Our Marie Curie European Training Network, FiBreMoD, is hoping to make use of its research into composite materials to reduce weight, fuel consumptions, and emissions. In the FiBreMoD project, we focus on fibre-reinforced composites such as carbon, glass fiber, or hybrids, which is a mixture of the two. As the name suggests, a composite material comprises of 2 or more constituents, in our case, reinforcing fibers, and a polymer matrix, which in turn is made from resin and a hardener. At the end of the curing process, we are left with a structural component, such as this one. This process is what gives fibre-reinforced composites specific properties that far exceed that of common metals. For example, replacing half of the steel parts of a car, such as bodywork and suspension components, with carbon fibre-reinforced composites will reduce weight and have a huge impact on fuel use and emissions. The average lifespan of a car is 200,000 kilometers, and over 60 million of them are produced annually. Taken together, this would mean CO2 emissions produced would drop by more than 10 million tons per year. This is a huge saving. These composites are therefore crucial for weight reduction throughout the entire transport sector, as well as in other applications. These include aerospace, wind turbine, sports equipment, and even reinforced concrete. Whilst they are currently widely used, carbon fiber composites are relatively new materials. We do not understand them as well as metals and concrete. Carbon fiber reinforced composites are very strong. For example, a single piece of carbon fiber the thickness of a ball-tip pen can support the weight of a fully grown adult. However, this performance comes with a price. They're incredibly complex. The complexity arises from a multi-phase makeup. This means that when components fail, they fail spectacularly. This component broke at roughly 3 tons, which means it would have supported the weight of a fully loaded transit van. Industry cannot take risks with safety. Therefore, many parts are over-engineered. This has a major cost implication, followed by weight penalties. Here's where the FiBreMoD project comes in. We're a community of 13 young researchers from all over the world, working across Europe and even down to Israel, in academic institutions, as well as 3 internationally recognized industry partners. Our aim is to push the boundaries of our knowledge on composite materials with direct implications in the industry. We do this by gathering input data for the models. We find the independent properties for the fibers and matrix and use them as base for our fiber break models. The better the data, the better the models. The difficulty in characterizing the constituents arises mainly from their small size, in the case of the fibers, and from the complexity of the polymers used in the matrix. Understanding these will help us to improve the accuracy of the prediction models significantly. We developed various strength prediction models. We can use these to run virtual simulations to try and more accurately predict the evolution of damage and subsequent failure of components and structures. We then test these models against the real material behavior to benchmark them. That is where the experimental aspect of our project follows. To assess the internal microscopic failure events that take place in such complex materials, we use techniques such as X-ray computed tomography. We use it to visualize how damage is progressing inside the composite material and, crucially, how the 2 components are interacting. As good as these machines are, they can be quite slow. A full test can take dozens of hours to run. This is where the project comes to the rescue again, giving us access to particle accelerators such as the ESRF in Grenoble, France, or SLS in Switzerland. These use synchrotron light as opposed to conventional radiation, and what takes hours or even days in a lab can now be done in seconds to minutes due to unique properties of synchrotron light. Such facilities are pushing the capabilities of today's engineering and physics to the absolute maximum. The final part of the project is to work with industry, Toyota, Siemens, Shomara, and Diastron, as well as other partner organizations that are an active part of the project. The job is to apply, verify, and eventually suggest improvements to the models for the use in a commercial context. This gives our project a strong industrial relevance. Our models are tested immediately on automotive components, pressure vessels, as well as other real-life applications. It is a big process with a lot of moving parts, but is important in helping further understanding and development of these materials. The technology will also help to reduce production costs and waste in the industry, as well as allow the design of safer, better composites for everyone to use.